ignore that for now. We'll get to that. I just got it up there. I'll just blank it out for now. Blank, blank, blank. Where's the blanker of that one? AVME. But since I don't want you to try to copy that monstrosity, et cetera, oh, look, it's the slides. Please enjoy. Random walk, that's right, yes. Basically, that's what you do if you had a few too many and you're trying to get to your car. And yes. But then somebody's stopping you from getting to your car because, of course, you're not going to drive in that state. And so you're going to turn over your keys. Alrighty, so more fun with stellar atmospheres. We were talking last time about various measures of temperature, and we mentioned how in thermal equilibrium, every measure of temperature is the same. If you're not in thermal equilibrium, they will give different results. And, you know, roughly speaking, the further away you are from thermal equilibrium, the more different measures of temperature can be from one another. But thermal equilibrium is the theoretical ideal situation that nobody wants to experience because you can't experience thermal equilibrium. You won't be there to enjoy it, would be where nothing's changing over time, which is not compatible with having an intellect because your brain is changing over time, right? So you never want to be in thermodynamic equilibrium. Anyway, but it's fun to study thermal equilibrium. In thermal equilibrium, every process occurs at the same rate as its inverse process. So, for example, ionization and recombination occur at exactly the same rates, so that the number of atoms with 2 electrons missing stays the same over time, except for statistical fluctuations. But in other words, there's just as many atoms with 2 electrons that are missing, being ionized to lose a 3rd electron, as there are atoms with 3 electrons missing recombining with an electron to become one with 2 electrons missing. Every process and its inverse happen at exactly the same rate, so that except for obviously statistical fluctuations, populations remain constant in time. In thermal equilibrium, every process occurs at the same rate as its inverse process. Every process occurs at the same rate as its inverse process. So all populations of energy levels and ionization states stay constant with time. I guess I'll say ionization stages. Ionization stages stay constant with time, except for statistical fluctuations. And the larger the sample of atoms or whatever, the smaller those statistical fluctuations will be as a percentage of the total number of atoms present. For any realistic size gas, you got like 10 to the 23 or more atoms around, and so the fluctuations as a percentage are quite small. Except for statistical fluctuations. Now, if you had an infinite amount of time, you can get arbitrarily large statistical fluctuations, but they'd be extremely rare. But y'all all ever heard of Boltzmann brains? Yeah, so the idea is, well, if you had a universe that could last forever, And it was in thermal equilibrium. Nevertheless, even in thermal equilibrium, you do get statistical fluctuations. And if you wait long enough, you can get arbitrarily large statistical fluctuations. So the argument is that if that's true, infinite universe lives forever, thermal equilibrium, it's more likely, says the argument, that what has happened is a statistical fluctuation has caused your brain to momentarily pop into existence with false memories of your life up to now, and you only last for a moment, and that's it, and it's just an illusion that you've had a life, and so on and so forth. You're more likely to just be a Boltzmann brain, a statistical fluctuation that self-assembles very rarely on occasion out of nowhere, just from, and then just as quickly will go away. Do I believe that? No, but it's a fun argument. Just thought I'd mention that. Anyway, so I try not to lose sleep over that. But if it is true, then I'm only imagining that I have tried in the past not to lose any sleep over it. Okay, so anyway, and as we keep mentioning before, also all measures of temperature are in agreement. So strictly speaking, because there's never a perfect thermal equilibrium, the temperature is never really perfectly well defined, but it can be awfully close to being well defined. Now we want to pop another important concept here out, which is mean free path. If the so-called mean free path, mean as in average, the mean free path, the average distance a particle goes between interactions, if the mean free path, the average distance between interactions, average distance a particle, which could be a photon, travels between interactions, like a collision or whatever, if the mean free path of a particle species, like doubly ionized carbon or electrons or deuterium nuclei, you could be, this could be any kind of particle species. If the mean free path of a particle species is much shorter than the characteristic distance over which the temperature changes appreciably, then this particle species will tend to thermalize with other particles in their vicinity, and we can get away with the assumption of local thermodynamic equilibrium for that species. The idea that that species is, in any given place, close to having a thermal equilibrium distribution, like its distribution of speeds would be the Maxwell-Boltzmann distribution for the temperature at that location. Now, if temperature is changing from place to place, again, it's never perfectly well defined, but if things are close to thermal equilibrium, then we can talk about local thermodynamic equilibrium, and if a particle species doesn't travel far compared to the distance over which that measure of temperature changes appreciably, then that particle, through collisions and interactions and so forth with other particles, ought to thermalize, ought to get close to being described by thermal equilibrium. So, if the mean free path of a particle species is much shorter than the characteristic distance over which the temperature changes appreciably, is much shorter than the characteristic distance over which the temperature changes appreciably, and you might already be formulating in your head, what do you mean the characteristic distance? And the answer is, there's no precise definition of that. You just have to kind of come up with something reasonable in each case. Over which the temperature changes appreciably. We'll give an example of a good definition of characteristic distance over which the temperature changes appreciably. Then this particle species will tend to thermalize with other particles in their vicinity. I'll say particles of this species will tend to thermalize. I like that word, thermalize. Will tend to thermalize with other particles in their vicinity. Via collisions or other interactions. So if you have a gas, if you mixed two gases at different temperatures, right? You got this container and you blow in gas at 100 degrees Celsius and gas at 80 degrees Celsius, and they mix together. What's going to happen? What happens in that case? Overall, do you still have, if you wait, do you still have some gas at 100 Celsius and other gas at 80 Celsius? No. What happens? Levels out, right? They come to an intermediate temperature. If the masses were equal, it's a good bet they'd come to the whole thing would mix and get to a temperature halfway between, 90 Celsius. May not be halfway between exactly. The thermal heat, the specific heat might be different at different temperatures, blah, blah, blah. But in any case, they'll come into equilibrium at some intermediate temperature if you do that. How do they do that? Well, the 100-degree gas particles are moving faster, and the 80-degree gas particles are moving slower. And they're going to start smacking into one another, exchanging kinetic energy in collisions, and as a result of that, things will average out. And they'll change into a Maxwell-Boltzmann distribution of speeds that is at that intermediate temperature, as opposed to two separate distributions at two different temperatures. In other words, thermal equilibrium arises if you wait and allow particles to interact with one another until they reach a situation of equilibrium. And so that's why we say that they're going to thermalize with other particles in their vicinity via collisions or other interactions. And so if particles are going, say, a centimeter between collisions on average, but the temperature doesn't change appreciably over a distance of like a kilometer or so, then a particle is going to undergo many interactions with other particles that are in a region that's all at about the same temperature. And so as a result, they will tend to reach a distribution of speeds, for example, for the Maxwell-Boltzmann distribution, that's characteristic of the temperature in their vicinity. By contrast, if the characteristic distance over which the temperature changes is a meter, and particles travel on average 500 meters between collisions, well, then they're not going to thermalize, because by the time they collide again, they've collided with particles that are in a region of a very different temperature from where they started. And so in that situation, you can't have this idea of local thermodynamic equilibrium that we're talking about here. What questions do you have? So, in this case, we say that local thermodynamic equilibrium, which would get really tiresome to say all the time, so we call it LTE, long-term evolution, right? 4G LTE. In this case, we say that local thermodynamic equilibrium applies for these particles. That you can get away with over small enough regions the idea that locally things are pretty close to thermodynamic equilibrium, at least for particle species where the mean free path is small compared to the characteristic distance over which the temperature changes. Can I erase this board now? Okay. Sometimes you have a situation where some particles can have LTE assumed for them, but others cannot. In other situations, well, you pretty much can say for all the particles LTE holds, and then it's a reasonable approximation to say, well, I can just use thermal equilibrium as an approximation for all the different layers in the star, for example. So let's talk about, well, what do we mean, this characteristic distance over which the temperature changes? One measure is the so-called temperature scale height. It's a very common measure. One measure of the characteristic distance over which the temperature changes appreciably over which T, I'll just start saying capital T, changes appreciably. This is a very common measure, is the temperature scale height. Very important in astrophysics, very important in meteorology. Temperature scale height, so we're going to call that H sub T, and its definition at any given point is it's the temperature at that point divided by the absolute value of the temperature gradient dTdr, if we're talking about a star where R represents distance from the center, or a spherical atmosphere. This could also be dTdx. It's just a derivative with respect to position. For us in astrophysics, that's often going to be dTd radius, because we're talking about how do conditions change within the star as a function of radius. And so that's a natural thing to use, is radius, to think of that. So first of all, is this a distance unit-wise? What are the units of temperature? And what are the units of dTdr? Kelvin per meter, right? So it's right, Kelvin meter. So it's kelvins over kelvins per meter. So the kelvins cancel, and you're left with meters. So unit-wise, yes, this is a distance. And what does it represent? Which is the distance over which the temperature would go from 0 to T if dTdr were constant. There's another better interpretation I'll give in a minute, but this is one way to interpret it as well, which is the distance over which T, well, I'll say temperature in this case, I'm going to go say from 0 to T. I don't want to say T would go from 0 to T. Over which the temperature would go from 0 to T if the absolute value of dT/dr were constant. Actually, I don't even have to say absolute value there, just if dT/dr were constant. And to see why that is, we make a plot here. So let's say here's R, and here is temperature. So this is not what happens in a star, but what if at some value, well, it would happen over small distances, but certainly overall the temperature gradient isn't going to be constant. But what if here's R equals R, well, it doesn't even have to be there. Here is R equals R naught, and here is, say, I can make it, it doesn't even have to be that. How do I want to do this? R equals R1, R equals R2. So two different radii. If I'm making a plot of temperature versus R and dT/dr is constant, what does that plot look like? It's a line, right? Slope is constant, right? And I'm going to make it decreasing with R because in a star, temperature decreases as you move away from the center. So what if that's what a plot of T versus R looked like, right? And, oh, actually, no, I wanted it to be, okay. So there's T, and let's say over here at R equals R2, that's where T is equal to 0. So we'll say at R1, temperature is T, I'm calling the axis T, and I'm also saying this is T, don't tell Dr. Nunemacher. So the temperature is T at R1, and T is equal to 0 at R2, right? Then if the distance between R1 and R2, if we call that HT, the distance over which the temperature goes from 0 to T with a constant temperature gradient. My line's a little bowed, but yours is going to be a perfect straight line in your notes. Okay. Then absolute value dT/dr, well, that's going to be the slope. Okay, I can use the two-point formula for the slope, right? The slope is the change in T over the change in R, right? So the slope is going to be delta T over delta R. What am I going to write for delta T here? T, right? I could do like, if you like, T minus 0, right, over R2 minus R1, because I'm looking for the absolute value, so, you know, it'd really be 0 minus T over R2 minus R1, but I'm taking the absolute value. I want everything positive. So T minus 0 over R2 minus R1 is the slope, but that's T over H sub T. So in other words, as advertised, that says that H sub T is T over dT/dr, absolute value in this case. So indeed, if you had a constant temperature gradient, if dT/dr stayed constant, then H sub T, defined by T over dT/dr, is how far away you are from where the temperature falls all the way to 0. Which won't happen, right? Stars don't have anywhere in them that is at absolute 0 Kelvin. This is just kind of math here. What questions do you have? Because next I'm going to give you what I think is a more useful understanding of what dT/dr represents in general, because typically, is dT/dr going to stay constant in magnitude? No, it certainly is not. It varies from location to location. So let's give another interpretation of what the temperature scale height means. put that? Oh yeah, okay, it's at the bottom of the page. Okay, another interpretation. Another better interpretation, more sophisticated, more general, to be applicable. If we assumed T equals T naught e to the minus R over HT, so that the temperature is decreasing exponentially with distance, which is liable to be the case more so than it would be just a linear function. And again, this isn't always going to be the case, but in a lot of situations you do get like an exponential decay like that. Then what's dTdr? Right, so if I made a plot like this, right, here's R, here is exponential decay, kind of looks like that, right? And so if so first of all, what's the value of R when T is equal to T naught in this formula? 0, right? So we would have, there's T naught, and you get an exponential decay, right? T equals T naught e to the minus R over HT. And if we didn't want it to be at R equals 0, this could be e to the minus R naught over HT to make it 0 at R equals R naught. If that's T, what's dTdr? What's that? Yeah, I literally mean, yeah, I want the derivative, right? What's the derivative of T naught e to the minus R over HT? Times minus 1 over HT, right? So this is the absolute value of T naught e to the minus R over HT times minus 1 over HT, just taking the rule for finding the derivative of an exponential function. But I'm taking the absolute value here, so I get just 1 over HT times T naught e to the minus R over H sub T. But what is T naught e to the minus R over HT? It's T, right? T at any R is T naught e to the minus e to the minus R over HT. So this is T of R over HT is equal to the absolute value of dTdr. So in other words, if you had an exponential decay, then HT is in fact, right, T of R over dTdr. But the point being then that it's the HT that appears in that expression. It's the HT that shows up in the exponential there. And since these exponential decays are going to show up over and over again for us when we talk about radiative transfer even, in other contexts, interpret what does the scale height represent? In other words, when R is equal to HT, right, if T is equal to T naught e to the minus R over HT, then when R is equal to HT, what is T equal to? Put in R equals HT, and what is T equal to? T naught over E. Yeah, T naught e to the minus 1. T is equal to T naught e to the minus 1 equals T naught over E. So HT is the E folding distance. In other words, the distance over which T falls to 1 over E of its initial value. But don't be under the impression that that only applies to T naught. In other words, for an exponential decay, no matter where you start, after one scale height there, after HT, you're 1 over E down from wherever you started. It doesn't have to be R is equal to 0, right? Because if you have I didn't think of like preparing this beforehand. Maybe you already realized this. Let's see, how would I show that, right? So if T1 is equal to T naught e to the minus R1 over HT, right? I just say, okay, at R equals R1, T is equal to T1. And at T2 is T naught T2, yeah, if I say, actually I'll do it like this. So T of R in general is T naught e to the minus R over HT. So what is T of R plus HT? Well, that's T naught e to the minus R plus HT over HT. That's T naught e to the minus R over HT times e to the what? So in general, T of R is T naught e to the minus R over HT. So T of R plus HT will be T naught e to the minus R plus HT over HT. Now I'm going to factor that exponential right there. So that factors into e to the minus R over HT times what? E to the minus 1, right? E to the minus HT over HT. Right? Because e to the a plus b is e to the a times e to the b. So I'm just factoring e to the minus r plus ht over ht is e to the minus r over ht times e to the minus ht over ht. So that's t of r times e to the minus 1. Or in other words, t of r over e. So no matter what value of r you start at, if you have an exponential decay, then after one scale height, the temperature has fallen to 1 over e of where you started, wherever that happens to be. If you add a scale height to wherever you started from, the temperature after one scale height is 1 over e of what it was at your starting point. this is the same sort of thing that applies with radioactive decay, except that here we're talking about a decay with distance instead of a decay with time. So with radioactive decay, after one half-life, what fraction of the atoms are remaining? Half. After two half-lives, what fraction of the atoms are remaining? Quarter, right? Half of a half. Because no matter where you start after one half-life, half of them disappear. After three half-lives, how many are left? An eighth, etc., right? So now, what about here? Because, we talk about half-life because it's easy to picture. You could also talk about the 1 over E life, the time it takes for only 1 over E of the atoms to be left. And here, we've got the scale height is the distance for 1 over E of the temperature to be left, so to speak. So after two temperature scale heights, if you go a distance 2 HT, the temperature has fallen by what factor compared to what it started at? What's that?
1 over 2E.
Not 1 over 2E.
1 over E squared.
1 over E squared, right? 1 over E times 1 over E, right? Just like 1/2 times 1/2. 1 over E times 1 over E. So after 2E folding lengths, you've got 1 over E squared of what you started with. After 3E folding lengths, you've got 1 over E cubed of what you started with, etc., right, etc. This is going to show up over and over again because not long from now, we'll have a bunch of photons trying to make their way through a gas that has opacity, and there'll be an E folding distance over which only 1 over E of the photons are still in the beam. Same sort of idea. And then we'll bring in the idea of optical depth and so forth. And so notice then too, what we're saying here is no matter where we start here, right, T over dt dr is always ht, and if that's a constant, then no matter where I am, I find the slope, I find the value of t, and t over the slope is the same for every point along an exponential decay. That's one of the things that's a special thing about exponential decay, that property that value over slope stays constant no matter where you are. And again, it could be versus time for radioactive decay or versus distance for a temperature decaying that exponentially, or photons being picked off as they try to make their way through a gas. And so you're losing photons along the way. And if absorption is constant, if the absorption coefficient is constant, you get something very similar. Okay? Questions, comments, observations? Yes?
For the second last one, what is the
Which one, here? Yeah, so here I'm saying that e to the minus r plus ht over ht is, well, that's the same as e to the minus r over ht plus ht over ht, right? Right? Does that make sense? Yeah, okay. Well, but then e to the a plus b is e to the a, e to the b. So I'm factoring this as e to the minus r over ht times e to the minus ht over ht. But quick, simplify. E to the minus ht over ht is also e to the minus 1. E to the minus 1. So that's an ht divided by an ht, in other words. Yes. Which seems like trivial, but no, that's what it is here. Yep. Okay. Other questions, comments, observations? Okay. So now let's talk about finding an expression for the mean free path. How far particles travel on average before they interact. And even that can be a little bit weaselly. Like, what do you mean they interact? If you have particles that are electrically charged, no matter how far apart they are from one another, they're constantly interacting with one another. And so you have to have some measure of, okay, well, what do you mean by significantly interact? So it's important to understand that with this thermodynamics kind of stuff like this, it's not always exactly clear-cut how you should define things like mean free path, and you have to come up with something that's reasonable. But for an ideal gas, the model we make classically, even though we know it's not literally true, is you might think of the atoms or the molecules as just being little hard spheres. In other words, they're billiard balls, microscopic billiard balls, and the only way they can interact is smacking into one another. So they literally have to collide with one another. Now, real hydrogen atoms, for example, are they fuzzy electron clouds or hard spheres? They're fuzzy electron clouds, right? And so, okay, how would we model those as hard spheres? Well, you can say, well, roughly speaking, if the atom's in the ground state, you could consider it a sphere whose radius is the Bohr radius, for example. And if they come within within two Bohr radii of one another, then they smack into one another and collide. And if they don't, you pretend they're ignoring one another. But that pretending they're ignoring one another unless they hit one another is the ideal gas law approximation. The ideal gas law assumes that particles only have elastic collisions with one another, and otherwise there's no potential energy of interaction. So we're going to make a hard sphere model of atoms and figure out if they were little billiard balls, how far would they go between collisions. To find the mean free path, to find the MFP, because that's another thing that gets tiresome to keep writing out. So to find the MFP, and I think it was Colgate that used to do this, and so whenever I see that, I think maximum fluoride protection. Because Colgate used to have ads on TV where they go, Colgate with MFP, right? Maximum fluoride protection, et cetera, et cetera. To find the maximum, mean free path, consider hard spheres of radius r. Hard impenetrable spheres. They're billiard balls. That's our model for our little atoms here. You know, for billiard balls to really collide inelastically, they would do something that you never observe. If billiard balls really collided with one another inelastically, what happens when real billiard balls collide that wouldn't happen if it was an elastic collision? They wouldn't make a sound. Yeah, they wouldn't make a sound. When they collide and make a sound, that's dissipating some of the energy. So we would need billiard balls that silently collide and just, they absolutely bounce back, but to bounce back with the same kinetic energy as coming in, no sound's allowed to be emitted. So our ideal gas, don't imagine little things going around, click, 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 click. But you know, how do we hear the clicks? It's through the air. If we're down at the atomic level, in between there's vacuum, so there's no medium for sound to travel, right? But just thought I'd point that out. So if you make a little movie, your movie better not have sound here. Little hard spheres of radius r. For an H atom in the ground state, we'd likely use R equals A1, the Bohr radius, anybody know, remember, what's the Bohr radius equal to, roughly speaking, in nanometers? Know your atomic sizes. How big's a hydrogen atom? It's fuzzy. It doesn't have a size per se, but you know what I mean. Whereas most of the electron cloud probability concentrated within, or if you took the Bohr model, what's the first Bohr radius? What is it? Do you remember? You should remember. Yeah, it's in the ground state. How big is a hydrogen atom? Oh, this should be in your things you just know so that you can make estimates of things.
1 nanometer?
Pretty close. For the diameter, yes. So I'll give it to you. Yeah, I'll give it to you. Or no, not close. Sorry. But not close. That's too small. That's a proton. It's 10 to the minus 15 meters. Proton's 10 to the minus 15 meters. A hydrogen atom is about 100,000 times larger than that. So therefore, how many meters? Instead of 10 to the minus 15, what's 100,000 times 10 to the minus 15? 10 to the minus, what's 100,000? That's 10 to the power of 5, right? 5 million 6. What's 100,000 then times 10 to the minus 15? 10 to the minus 10, or in nanometers, 10 to the minus 10 meters is how many nanometers? What's a nanometer? 10 to the minus what meters? 10 to the minus 9, so 10 to the minus 10 is how many nanometers? 0.1, yeah, so it's about 0.1 nanometer, right? 0.1 nanometer. The Bohr radius is about a 20th of a nanometer. If I recall correctly, it's like 0.053 nanometers, I think. So in other words, about a 20th of a nanometer, so that the whole diameter is about a 10th of a nanometer. That's a characteristic atomic size. Because now there's atoms that are larger. I think francium turns out to be the largest atom. But what happens when you add more protons in the nucleus is you attract more electrons, but the nuclear charge is bigger. And so, as a result of that, yeah, you add electrons, and that would cause the atom to get bigger, but the nucleus is attracting them more strongly, which works in the other direction. So, a 10th of a nanometer is not too bad for atoms in general. So that's kind of the thing to have in your mind. It's like maybe a few tenths of a nanometer for big atoms, more so. But anyway, time for a break. We're going to collide those things, see what happens. Well, not literally. Yes? Of its initial value, wherever you started from.
Is that for, what's that for?
So that's what the scale height represents on the assumption that you've got an exponential decay of temperature with distance.
So that's
what?
That's how it would decay if I went over E.
Yeah, over a distance ht, it is 1 over e of its starting value wherever you started. So if at some location the temperature is 1,000 Kelvin, after one scale height the temperature is about roughly 300 Kelvin, because 1 over e is about a third, right, et cetera. So it falls by 1 over e is 1 over 2.78, blah, blah, blah. So that's the idea, that, you know, if it's 100 Kelvin here and the scale height is 1 meter, then over here, if this is the direction of decreasing temperature, 1,000 Kelvin here it's like 300 something Kelvin, right? Because it's 1 over e of that. 1 meter more, and it's more like 100 Kelvin, because I've gone 2 e-folding distances. And then over here, 3 meters away, it's down to like 30 Kelvin, and so on and so forth. Just keeps going and going like that.
So we are modeling temperature decay over a given distance.
Yeah, so we're looking really for a measure of what it means to say the distance over which the temperature changes appreciably. And so one measure is to take the temperature divided by the temperature gradient. And that, again, if the temperature were decreasing linearly with distance, that would be the distance over which the temperature would fall to 0 from wherever you are. After that distance, the temperature would be down to 0 if the slope stayed constant. If the temperature is an exponential decay, then it's the e-folding distance that you get out of that, the distance over which the temperature falls to 1 over e of what it is at your location that you're picking out here. But in general, HT, we can use it as a measure of about how far we would call a distance over which the temperature changes appreciably.
Two things.
Yes?
This is the 14th time you use the word appreciably in last 50 minutes.
Okay. I appreciate your pointing that out. Yes?
And what determines if it's falling exponentially or linearly?
Whatever the conditions that we're in. So it can definitely, like it shows up in atmospheres a lot. It turns out the physics works out that often you get an exponential decay of temperature with height, but not always. So it's going to depend on the environment that you're in.
How does it work for the stars?
It often, in some parts of stars, you'll also get that some parts, yeah, not necessarily everywhere. So for example, if a star, the central regions of the star are nearly isothermal typically, for example, the temperature's not changing much at all. So I'm not claiming that, oh, temperature is always falling exponentially. It's just that it turns out that it often happens that you get an exponential fall off with location. Right, yeah. So we'll see examples of where things like that might arise. Yep, so just gotta take my word for it. We'll see all this kind of stuff later. All right, so maximum fluoride protection. Let's get the mean free path here. So two particles collide if their centers pass within 2R of each other. Right? Because here's one particle, here's the other particle, and for them to just smack into one another, they would have their centers in a glancing collision like that 2R apart. So if their centers get within 2R of one another, or if you extrapolate, right, they're far away from each other, and if they weren't going to collide, their centers would pass within less than 2R of one another, then they're going to collide because at some point their centers will be within 2R of one another. If they're on a collision course such that their centers would pass within 2R of each other, they will collide. And this allows us to make a nice simplification where instead of trying to keep track of a bunch of particles of radius r, we say, okay, well, let's consider one particle whose radius is 2r, and all the other particles are just little points. So the other particles are just represented by a point at their center, and our particle has radius 2r, such that if that thing of radius 2r hits any of the points, that's a collision with another particle. So, simplified description. Single particle of radius 2r, and by that I mean its radius is whatever, but its radius is also twice the radius of the actual particles. We're making a new particle whose radius is twice the radii of the actual particle. So r there isn't that particle's radius. That particle's radius is 2r. I'm not using r to mean this particle's radius. I'm using r to mean the radii of the real particles, right? Got it? That's the point there. Don't be confused. I forbid you to be confused. And our particle is moving along. If you think about it, if I have a basketball, say, and I'm moving along here, and you think of the volume that's sweeping out, it's sweeping out some cylindrical volume whose radius is equal to the radius of the basketball, whose diameter is equal to the diameter of the basketball. So, here it is. Here's some volume that it has swept out, moving along. It's moving along at some speed v. And I think I'll just draw it like this to kind of emphasize that 2r is the radius of this cylinder that it's sweeping out. A sphere of radius 2r moves with speed v through a collection of stationary points representing the centers of other particles. And then we just have to see, well, how many gnats does it collide with, right? I throw a basketball through a bunch of gnats that are just hovering there. How many gnats does it smack into? That's, each one's a collision. Through a collection of points representing the centers of other particles. The gnats even don't have to be just hovering there. They could just be flying around as long as there's some like density of gnats per cubic meter. Points representing the centers of other particles. So VT will be the distance traveled in time t. So I'm saying here is the cylinder it sweeps out in a time t. It's of length VT and radius 2r. Particle travels a distance vt, so it sweeps out a cylinder in time t, whose length is vt, whose radius is 2r. And we're going to talk about the collision cross-section. Actually, I'm going to capitalize that because it's a very important concept. The collision cross-section, sometimes called the collisional cross-section. The collision cross-section of our hard sphere atom is, we use the symbol sigma for that. So its collision cross-section is literally its cross-sectional area. If you imagined you were instead shooting a bunch of particles at it, like you're firing BBs at it, they hit it if they fall within its cross-sectional area when they reach it. They miss it otherwise. So its cross-sectional area is going to determine the fraction of atoms that hit it. If there's a certain number of incoming atoms per square meter, its cross-sectional area is going to determine what fraction of those atoms actually hit the basketball. So turn it around. If it's flying through the BBs, the same kind of logic applies. So what's the cross-sectional area of a sphere of radius 2r? Ah, but wait a minute. It's what it looks like. This is kind of like when we were talking about solid angle. If you want the solid angle that the sun subtends at our location, it's not the sun's full area. It's what it looks like it has as area to us. In other words, what does the sun look like to us? It looks like a circle, right? It looks like a circle for these purposes. Put another way, a plate, a circular plate, would smack into just as many atoms as a sphere would, right? Because what matters is the cross-sectional area. And by the way, I want to draw here, here's those centers, right? So here's a bunch of atomic centers just distributed around, but there'll be some number density, some number per cubic meter of them. So I didn't draw in the points before. So its collision cross-section is pi times 2r squared, because its cross-sectional area is pi times 2r squared. And again, 2r is its radius, right? So it's pi times its radius squared, but we're calling its radius 2r. R does not stand for its radius. Again, don't be confused by that. R stands for the radii of the true particles, and its radius is twice that. So sigma times 2r, sigma is pi times 2r squared. Does that make sense? Happy, not happy? You don't look happy. What are you not happy about? Okay, so got a basketball, right? And there's a bunch of gnats in here. And it's going to keep smacking into a bunch of gnats as I walk along, right? Would it make any difference if I had just a plate of the same radius? I walk along with a plate. Well, the plate is also sweeping out that same volume. So that's why it's the cross-sectional area, because it looks like a circle to us. It's the cross-sectional area. Take a slice through the equator, the cross-sectional area that matters, and the area of a circle is pi r squared, right? But this one's radius is 2r, because we're not calling r its radius. Its radius is 2r. We're using r to mean half of its radius here, because we're modeling the other particles being point particles, right? The idea is you get a collision as long as the centers pass within 2r of one another. So we could either have a bunch of particles that really are of radius r, or one particle of radius 2r, and we just see if it hits their centers. So if their centers pass within 2r of its center, that's the same thing. Does that make sense? Okay. What other questions do you have? So, in time t, the moving atom, or whatever kind of particle it is, the moving particle sweeps out volume. So, what area is that right there in terms of other symbols I've been using? I want to be sure that you're clear on this. The area of a face of this cylinder is equal to what? And that we have called? Sigma. It is sigma, right? So that's sigma. That's area sigma. That's area sigma. Our cylinder has area, cross-sectional area sigma, its length is VT. Oh my God, if you've been doing Gauss's law problems in E&M, you can tell me what the volume of that cylinder is. Yeah, sigma VT, right? Area times length is the volume of the cylinder, right? And so it sweeps out volume, sigma VT. Sigma VT and I should also add here the number density of particles is, what symbol we typically use for a number density? N, capital N or little n? Lowercase n, right, is n. So there's n particles per cubic meter. So our particle in time VT sweeps out volume sigma VT, right? So how many particles did it collide with? If there are n particles per cubic meter, and it swept out sigma VT cubic meters, how many particles did it collide with? If our particle swept out sigma VT cubic meter, the volume of the cylinder, right, and there are little n particles per cubic meter in the gas, or whatever we're talking about here, probably gas, how many collisions did our particle have? How many gnats did the basketball sweep up? If there's n gnats per cubic meter, and the volume swept up sigma VT cubic meters, how many gnats did it sweep up? Yeah, and sigma VT, right? Number density times volume is number, right? Sweeps out volume sigma VT, colliding with n sigma VT atoms. Colliding with n sigma VT atoms. Particles, I should say, because maybe they're molecules. Particles, other particles, I'll call it. So our particle in time t smacked into n sigma VT other particles. And now we have everything we need to figure out the mean free path. So the mean free path MFP, registered trademark, is, we'll say that's L equals VT over n sigma VT, because that's going to be distance over number of collisions, right? If it traveled 1 meter and collided with 1,000 particles, on average it travels 1,000th of a meter between collisions. If it traveled 1 meter and collided with 10 particles, on average it traveled 1/10 of a meter between collisions. So distance traveled over the number of collisions is the average distance per collision. That's the average distance per collision. Oh, but wait, can you simplify VT over n sigma VT? Anything cancel there?
It's 1 over n sigma.
Yeah, it's 1 over n sigma. In other words, L is just 1 over n sigma. So it depends both on the number density of particles, which makes sense. More particles means more collisions. And it depends on the cross-sectional area. The cross-section, bigger particles means more collisions, and therefore a shorter distance between collisions on average. So it makes sense that n and sigma should play a role, both of them. A more careful treatment yields L is equal to 1 over n sigma root 2. Which comes from the fact that, well, the particles are all moving around at different directions and so on and so forth, so it's a bit more complicated than our model, but we got pretty close to the right answer with our simplified model here. Yay, envelopes and their backs, which we can do calculations on. Right. What questions do you have? So, more particles in every cubic meter shortens the mean free path. Makes sense. If there's more particles around, you're going to collide more often. Shorter distance between collisions. bigger particles you're going to collide to. The bigger the targets, the more you're going to collide. So it's not unreasonable that both of those things should appear like that. In the homework, you'll joyfully explore, so what's the mean free path for, say, nitrogen molecules in our atmosphere? And you'll find it's actually quite small in human terms, but it's quite large compared to the molecules themselves. It's a fun little problem. You'll enjoy it. Woo! That's right. Yes! Yes! Nitrogen! What fraction of our air is nitrogen? Is it? That's like 78% nitrogen. Yeah, it's like 77, 78% nitrogen, something like that. Yeah, it's mostly nitrogen. Yes. Yep. Okay. Stellar opacity. Stellar opacity. So now let's apply this to photons innocently trying to make their way out of a star. But they could also be photons innocently trying to make their way through Earth's atmosphere. Or photons innocently trying to make their way through an interstellar cloud, or whatever. But stellar opacity, the same principles apply. Consider a beam of radiation traveling through a gas. So this is like a pencil. The limit of the solid angle of the beam goes to 0. It's a little pencil of radiation. And if there was no gas there, every photon's just like, I'm just going to keep on going and make it all the way. But if there's a gas there, then it's like, photons like, yep, I'd really like to make it to that back wall, but I got scattered in some different direction. I'm no longer in the beam. Or, yep, I'd really like it to make it to the back wall, but oh, an atom ate it. It's gone. So not all the atoms make it, right? And the idea will be here that, so imagine lots and lots of photons, and some of them don't make the journey because they get scattered or absorbed, but some of them make it through the gamut and get to the back wall or our telescope or whatever, right? And the more photons there are, the more that are getting absorbed or scattered along the way. Twice as many photons means twice as many get absorbed or scattered. And the more atoms that are around trying to eat or scatter those photons, the more that will get scattered, so on and so forth. So we're going to write down a relation that will describe that idea in just a moment. First, we will say that any process that removes photons from the beam is called absorption. Which is a bit of a confusing terminology because it means that because we're astronomers and we're weird and we can never make anything, it means that absorption is going to include true absorption, where photons are actually eaten by atoms and cause upward transitions, and scattering, where they're redirected, they're just moved off in a different direction. It's all going to be called absorption. So absorption is absorption and scattering is absorption is kind of what I'm saying. But wait, absorption is a tautology. So to fix that, we say, well, true absorption is absorption, and also scattering is absorption. Yes, that's weird, but we're astronomers. We do these things. So, absorption includes true absorption, in which photons cause upward transitions of electrons and disappear. Bye-bye. You gone. And scattering in which the direction of travel of the photon changes, but the photon does not disappear. I'll say in which the photon changes direction, but doesn't disappear. It's a hazy day on Earth and you just can't see those distant mountains very well. It's because of absorption and scattering of the light on the way from the mountains to your eyes. And so the further away they are, the more photons are lost. And the more haze there is in the atmosphere, the greater is the absorption coefficient. It's a smaller distance over which a given number of photons would be lost, etc., etc. Kathleen, you have that look of, what did he write? Yes? So, between which? Let's see. Here? Cause upward transitions. Might I recommend? Oh, okay, okay. But wait, do I not recall that a trip to an optometrist is recommended for your future? Yes, just saying for a little bit of self-defense here. Yes.
Sorry.
Quite all right. I do want you to be able to, yep, no problem. Anybody else? Anybody else want to complain? Huh? 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 Yeah? What? Okay, fine. Too bad. Sit closer. Here's a seat for you, right here. Okay. Let's write down how we describe this mathematically. Absorption is described mathematically via this. We say di lambda, the change in the specific intensity of the beam because of absorption, is equal to minus kappa sub lambda. So please note that this is a Greek letter kappa, not a K. So I don't know how you draw them, but you got to make it something that doesn't look like a K. That's a Greek kappa. Minus kappa lambda times rho, the mass density, kilograms per cubic meter, times I lambda times ds. So here, I'm just going to write it over here because I want to decorate my equation underneath it, and because my camera is not set to zoom to the whole blackboard, so I would write it to the right, but I'm not because of that. So ds is distance along the beam in the direction of travel. In other words, talk about a little distance ds you've moved along the beam. Distance along beam in direction of travel. The way the photons are moving, the ones at least under consideration here, the ones in the beam. And kappa sub lambda is the absorption coefficient, aka the opacity, the absorption coefficient, aka, what's aka? Yeah, also known as the opacity, right? Because if something is opaque, you can't see through it. My dad was very fond of, not in those words, but he would like to point out that I was opaque. Because he would say, when I would stand in front of the television, that I made a better door than a window, right? Another way to say it is, son, you are opaque, not transparent, right? The absorption coefficient, aka the opacity, its units are meters squared per kilogram. Meters squared per kilogram, and what that represents is cross-section per unit mass. Like interaction cross-section per unit mass. Because before, when we had our hard sphere, we said, what's its cross-sectional area? And that was related to how good it's going to be at intercepting, if you will, other atoms. And so we're generalizing this idea of cross-section here. If you had hard sphere atoms and you just said if the photon comes within its radius of its center, the photon gets absorbed, then its interaction cross-section would literally be its cross-sectional area. But really, atoms are fuzzy things, and so we'll get to it, but you can define precisely what you mean by the collision cross-section. For now, think of it as a measure of how big the targets look, the atoms look to the incoming photons, and we'll be more specific later. Units are meters squared per kilogram, i.e., that's an IE right there. You'll never know, but that is an IE. I'm just telling you right now, IE, interaction cross-section per unit mass. Interaction cross-section. I don't want to say collision here because photons, we don't necessarily think of them as colliding with the atoms. Interaction cross-section per unit mass. Different substances have different affinities for absorbing photons, and so they'll have different absorption coefficients associated with them. And there's more to it than that, as we'll see. The absorption coefficient depends on a number of things. And so let's kind of draw arrows that justify things here. So first of all, why is I lambda over there on the right-hand side? It's because the more photons there are in the beam, the more of them that are going to be absorbed in any given little distance along the beam. If there's twice as many photons that could be absorbed, twice as many photons will be absorbed. If there's a certain probability that any given photon will be absorbed in the next meter, then having more photons means more photons being absorbed in the next meter. So I lambda is there because the more photons there are, the more will be absorbed. The more photons there are, the more will be absorbed. Where, of course, absorbed means truly absorbed or scattered, right? This silliness, right? The more will be removed from the beam. The more photons there are, the more will be absorbed. That's why I lambda is there on the right-hand side. It's representing that fact. And this is wherever you are along the beam, right? As you move along the beam, more and more photons are disappearing. It's going to be, in other words, we'll see there's a natural tendency for this to produce an exponential decay with distance, because it's analogous to atomic radioactive decay, where there's a certain probability per unit time of every given atom decaying, and that leads to an exponential decay in the number of atoms. Here, we'll think in terms of a probability per unit distance of a photon disappearing from the beam, which will lead naturally, if that stays constant, to an exponential decay in the number of photons along the beam as you move along the beam. This is what happens in a fog, typically. It's why, as somebody walks away from you in a fog, they disappear because a smaller and smaller fraction of their photons are getting to you instead of being absorbed or scattered by the fog particles. And it's the same sort of deal. If they move twice as far away from you, it'll be an exponential decay. It's you know, that sort of thing. So anyway, rho, we can think of rho being there, the mass density. Mass density is here because more atoms means more absorption. So it's not unreasonable that that should be there. More atoms trying to absorb photons means more of them will be absorbed. And if we think of our beam as like a pencil, if the density doubled, there'd be twice as many atoms per unit length as before. And so it makes sense that rho ought to be there for that reason. Why is there a minus sign right there? Yeah, because the number of photons is decreasing. So di lambda, the change in the number of photons within ds should be negative. It should be right? So I lambda is decreasing. So that's why there's a minus sign right there. All that kind of good stuff shows up there. And so I'm going to go beyond a little bit because I've never done this before. I've never explained this before in class. I don't know why. Y'all are special. Normally I would just keep going from here and do some other stuff next. I'm going to throw some more stuff in here. So let's think about this then. So first of all, if we look at all the units, right? So I've got kappa lambda rho ds, which is going to show up as d tau, the change in the optical depth in a minute, but, or maybe not a minute, it might be 2 days from now. But in any case, let's look here, because unit-wise, right, the units of I lambda and di lambda cancel, right? So everything else better be dimensionless. Kappa lambda times rho ds better be dimensionless to make the units work out, because the I lambda units, which is, remember, joules per second per square meter per steradian, those cancel out on both sides. So let's look at that. Units. What's the units of kappa lambda again? Meters squared per kilogram. Meters squared per kilogram. How about rho? Rho is, nope. It's the mass density, kilograms per meter cubed, yeah, kilograms per unit volume, right, mass per unit volume. So that's kilograms per meter cubed. What's the units of ds? Meters. Did everything cancel out? Sure did, all the units cancel. That's great. But let's look here. So yay, yay, cancellation. That better happen, it did. Otherwise we'd have a non-starter here. So I've mentioned that before to people, but here's what makes y'all special, okay? So let's look at kappa lambda rho. For kappa lambda rho, we get square meters per cubic meter. Yeah, it's 1 over meters, but more importantly, it's better to think of this as square meters per cubic meter. Or in other words, interaction cross-section per cubic meter. Just like pressure, right? Pressure is newtons per square meter. It's also joules per cubic meter, but that's not very useful to think of pressure as joules per cubic meter. It's more useful to think of it as newtons per square meter. And energy density, joules per cubic meter. It's also newtons per square meter, but that's not what it is physically, so you know, same thing here. Yeah, this overall cancels out to be reciprocal meters, but it's better to think of it as cross-section per cubic meter. Interaction cross-section per cubic meter. And here's why. Consider you've got this beam of photons, and we're going to consider part of it that's 1 meter by 1 meter. So a bunch of photons all traveling in the same direction, 1 meter by 1 meter across. How many square meters am I looking at? Yeah, 1 square meter, right? Not trying to trick you. 1 square meter there. And if, again, we think of the particles as little spheres that are desiring to eat the photons or kick them to the curb, one way or the other, then the idea would be, I've got, oh my God, I have to draw all these. Okay. There's a bunch of little thingies there. Each one of them has that little cross section there. That's collisional cross section, or that interaction cross section. And I'm just looking at, I'm just looking at the particles that are in 1 cubic meter. So if you're a bunch of if you're a photon and you're saying, you know, I'm trying to make it to the other wall there, okay, you and your friends, right, you're all trying to make it to the other wall there. Ah, Jim, I'll miss you, right, as you're going along here, right? You're all trying to make it there. Consider all y'all flying through 1 square meter, and then 1 meter of length. That's a cubic meter there, and there's little atoms or other particles trying to pick you off. And so here they are. They're really, in other words, I drew them all in the plane of the board, but they're hovering everywhere. You're just looking at the ones that are within that 1 meter distance in front of the board here. Right? Does that make sense what I'm saying here? Okay. So what's the probability that any one, we'll call them atoms, what's the probability that any one atom will pick you off? And by the collision cross-section here, we're saying it's an effective area such that if the photon hits that area, it either scatters or is absorbed. So it's gone from the beam. That's what sigma represents, that if it's an effective area such that if the photon lands within that area, he is gone, right? If a photon hits within an atom's cross-section, sigma, it goes bye-bye. It goes bye-bye. Aw, poor little photon. It was trying so hard to have just one dream. And no, stupid atoms. Just, no, we want this. We wouldn't want the core to shine directly on us from the center of the sun and all that, right? But still, okay? So, probability per atom that a given photon goes bye-bye in 1 meter of path along the beam is thus, so see if you can figure out. So again, I should point here, right? So atoms within 1 meter cubed of beam. So imagine 1 meter of length perpendicular to the board. Page, you're not writing on a board. Page. And the photons are traveling this way. The photons are traveling perpendicular. Photons, just being sure this is all in here so you don't look later and like, what was this? Photons moving perpendicular to the board. And by the way, if you're ever a particle physicist, you'll be glad that I explained this to you. Or if you ever take a particle physics course, you'll be glad I explained all this to you when you're trying to understand what cross sections are in particle accelerators and stuff like that. This is all the same kind of idea here. And then we even have differential cross sections, which are cross section per steradian as a function of theta, the scattering angle. Okay, anyway, probability per atom that a given photon goes bye-bye in 1 meter of path along the beam is thus, well, what would it be? So if we have all these atoms here, what's the chance that I'm going to hit any one of them, given there's a total of 1 square meter here? What's the chance I hit one of them if its area is sigma?
Sigma divided by number of particles?
You're on the right track, because in the end we would also include for the total number getting scattered the flux, the number of incoming particles per square meter. Okay, but what's the chance in this square meter of a photon going bye-bye? In this square meter, so consider this one right here. If the photon lands there, if it passes through here, does it get scattered by that atom or absorbed by it? Nope. How about here? Nope. How about here? Just this atom right here? Nope. 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 Yep. Okay. So the chance that I'm going to hit that atom will be the total fraction of the area that it covers, which is sigma over 1 square meter, right? In other words, sigma over 1 square meter is the probability that a photon will hit any one of those particular atoms. That's why the cross-section is what it is, essentially. It's telling you what's your chances of interacting with that particular atom. It's the cross-section it presents to you. So even if it's not a hard sphere, if you can somehow calculate the probability that a photon will interact with that atom, the probability per atom of interaction within any 1 square meter of beam, you could call that the cross-section. That's what we normally do, is, in other words, it's not literally a cross-sectional area like a hard sphere. It's the thing that makes the probability equal to the cross-section. You're defining it that way. It's an effective area that it shows. It's the area of a hard sphere that would have the same probability of interacting as the real fuzzy atom does, that where the probability falls off with distance instead of being 100% within and 0 without. And so, it's time to stop. So next time I'll complete this argument. So So look at it before we start next time, so it's not lost to your head or whatever. But we'll justify then the idea that it should be, in fact, kappa lambda rho ds that shows up as how many the fraction of photons that get absorbed or scattered is what it comes down to. Yes? What's that?
Is that going to be on the exam?
Yeah, let me think. Yeah, this could still be on the exam because we're not, yeah, it could. Yep. Yes. Yeah. Yep, because this is 9.2. Yeah, 9.3 is the equation of radiative transfer, which we will joyfully cover next week, but won't be on the exam.
So it's just up to show 9.2.
Up to 9.2, yes, 7, 8, and 9.2. Or in other words, the last 3 homework sets, yeah. The last three homework problems due on Friday, and all the other ones since assignment 4 are the ones that are fair game for similar stuff showing up. Oh, and I need to say, this building, did you guys get the email that said they're going to turn the power off in this building at 5 o'clock? No. Okay. Yeah, they didn't tell you all that, they just told the faculty that. Great. Yeah, so the power's going off at 5, so if you plan to be here at 5, use your torch, so to speak.
Write the place down.
Yep, that's right. It also means, is anybody coming to my office hours? Let me ask that. Oh, I get to cry. Okay, so, okay. I will not be here after 4:55 or so because the power's going to go out. So if you're coming, come before 4:55 or so, and I'll be happy to work with you. But after that, I ain't sticking around in a dark building. That's the story then. Yep. Yes. Was that? About 2 hours. And they didn't say why, but I have a guess, and that it's, we have the new Discovery Center, right? I'm guessing that it's to put that online. That's my guess. I don't know. Maybe it's because they think my computer should stop doing their calculations. They're really sick of it, right? But I don't think that's it, even though that's going to happen. Because my UPSs won't last for 2 hours. They last for 12 minutes at how hard those computers are running. Anyway.
Discovery Center.
Oh, all this dust they've been, so it's basically for the biology folks. So it'll be not only like, animal room, like we have a smaller one now, but other stuff as well. Yeah. So unfortunately there won't be any physics discovery in there, but there'll be, and it was going to be called something else before, but Discovery Center sounds much cooler and friendly, and so that's what they're calling it. Yes. What's that?
Where is it going to be?
In the loading dock area.
Okay.
Yeah, so in other words, right, remember when in the summer we would go through the loading dock and let Julia in, right? It's in that area. Yeah, that's right. It's still a loading dock, but beyond that, they've been making dust, and it's great because our department gets to enjoy the consequences of the construction, but doesn't get to use the actual facility. But, since we're such good people, we're happy for our friends in biology. Yes. Ah, there you go. Yes. Yes.